Hello everyone, I'm Mingqi Jiang. I will introduce our work on comparing the decision-making mechanisms by transformers and CNNs via explanation methods. Attribution map approaches highlight important areas in an image for deep network classification. It has been researched for many years, and there are many different types of attribution maps. Attribution map approaches only find one explanation for each image. In 2021, our group proposed a search-based method, structural attention graphs, that conducts a beam search to locate multiple part combinations that the network would predict with high confidence. We call them different explanations of the image classification. Past explanation work reveals that CNNs may be classifying some images based on a minimal number of parts. As shown in this example, the rightmost image with only a small part revealed is classified by the CNN with high confidence, while the middle image with only those parts masked have a confidence close to 0%. This raises several questions. How often does this happen? Does this apply to all models, including transformers? Do CNNs and transformers use similar or different features for classification? Previous explanation algorithms mostly explain a single image and only generate anecdotal evidence, which doesn't help to answer the questions we posed. In this paper, we propose the idea to apply those explanation methods on a large set of images, which potentially help us to get a more systematic approach to compare network structures. A main result we found out is that model behavior falls into two categories. ConvNeXt and non-distilled transformers are much more compositional, building confident classifications jointly from multiple parts, where removing some parts may only slightly reduce the confidence. In contrast, CNNs and distilled transformers behave more disjunctive, requiring very few parts for a highly confident prediction, but can rely on multiple diverse combinations for a confident prediction. We propose two approaches in this work. The first is sub-explanation counting. We divide the image into non-overlapping patches. A MSE is a minimal set of patches achieving over 90% likelihood compared to the full image. Then we construct a tree for each MSE by deleting one patch at a time. The number of sub-explanations is the number of nodes with classification confidence above different thresholds. To evaluate the similarity between models, we developed a second methodology called cross-testing, using one deep model to generate an attribution map and then submit the masked regions as input to the second deep model. If two models rely on similar visual features, then they should score highly in cross-testing. We used the first 5,000 images from the ImageNet validation dataset for all experiments. This is the results of beam search to locate MSEs. The numbers on the top right are thresholds used to count sub-explanations. Most CNNs, commonNeXt, and distilled transformers have higher MSE counts and smaller MSE sizes, while undistilled transformers have smaller MSE counts and larger MSE sizes. One interesting aspect is the significantly higher number of sub-explanations in commonNeXt and undistilled transformers. We examine which design drove this high number. Firstly, we trained commonNeXt and SwingT with smaller kernel and window size. Reducing the receptive field size decreased the number of sub-explanations by about 40%, but this did not fully explain the differences. So, we replaced the original layer normalization with batch and group normalization, and further trained models with different normalizations and smaller receptive fields. Surprisingly, changing layer normalization to batch normalization significantly reduced the number of sub-explanations by about 80%. Less sub-explanations drive models to disjunctive behavior, which are robust to occlusions by using a different conjunction if a key feature cannot be seen. In contrast, compositional mechanisms can also handle the occlusions, but with a different mechanism, where removing some patches only slightly lowers the classification confidence, creating a significant amount of sub-explanations. And the normalization layer significantly impacts model behavior. Batch normalization leads to disjunctive behavior, while layer and group normalization lead to more compositional behavior. For cross-testing, we use IGOS++ to generate heat maps. To better visualize these similarities, we applied kernel PCA to project all models to 2 dimensions, based on insertion score similarities. Models of the same type use similar features for their predictions. We can roughly delineate clusters of older CNNs, newer CNNs, ConvNeXt variants, non-distilled and distilled transformers. And distillation brings transformers closer to CNNs. In this paper, we find that different types of visual recognition models exhibit quite different behaviors along the concept axis of disjunctivism and compositionality. The choice of normalization strongly affects the compositionality of the model. With cross-testing, we found the same type of models use similar features for their predictions. There are significantly more results that we cannot show in this short 5 minutes presentation. Please check out our paper, as well as coming to the oral presentation and poster for more discussions.